Okay, so right now we're just looking at an example of a problem that we were going over last week. So this equation right here, x to the 2/3 power plus 4x to the 1/3 power plus 2 equals 0. This is something that we can manipulate to look like a quadratic equation. And so here I would look at and see that this is x to the 1/3. And I'm going to manipulate this first term to look like that. So I'm going to use the fact that I know power to power. So if I have b raised to the m power and that's raised to the nth power, I know that the rule is multiplication. So I'm going to kind of rewrite this going the other direction. Or no, going from multiplication to power, because I want an x squared, but I also want the square to be outside, and I want this piece in here to look like x to the 1/3. I'm already having problems with it not. So if I rewrite this as x to the 1/3 and then quantity squared, again, power to power is multiplication. So this is now x to the 2/3 plus 4. And then we have this x to the 1/3 plus 2 equals 0. So if we choose u to equal x to 1/3. So if we go back in here and we plug this in wherever we see an x to 1/3, we now have a quadratic. And so we have here u squared plus 4u plus 2 equals 0. So it's a quadratic. Now I would try to first factor it, but there's no two numbers that multiply to give you 2 and add to give you 4. And so I could complete the square, but I would prefer to use the quadratic formula. So u is equal to negative b, so negative 4 plus or minus, couldn't decide, square root b squared, so 16 minus 4 times a, which is 1, times c, which is 2, all over 2a, so 2 times 1. So let's just clean it up. Negative 4 plus or minus the square root. Well, 4 times 2 is 8, so 16 minus 8 is 8, all over 2. Let me see what we're doing. Let's, again, clean this up a little bit. And we can look at the square root of 8. We can pull a piece out. Square root of 8 can be written as square root of 4 times square root of 2. And so this is 2 root 2. So we get negative 4 plus or minus the square root of 8, which is 2 root 2, all over 2. So this is like two separate fractions. We can break it down. We can think of it, or we can think of it as pulling out a 2. So if I pull out a 2, that would give me negative 2 plus or minus root 2 all over 2. And so now we have like factors in the numerator and denominator. And so we get u is equal to negative 2 plus or minus root 2. But again, we didn't have u in the original problem, and we want to know what x is. But we've manipulated this, so now we can find x. So we said that u is equal to x to the 1/3. And so if I go back in here and I rewrite u here with x to the 1/3, I could now solve for x. It's going to actually come down here now. So I get x to the 1/3 is equal to negative 2 plus or minus root 2. So I don't want x to 1/3, I want just x. And so clear the cubed 1/3. We can cube both sides of the equation. using the rule that power to power is multiplication, and 3 times 1/3 is going to give us a 1 as our exponent, and cube this. And so we have technically 2 separate things. We have x is equal to -2 minus √2 quantity cubed. And I have x is equal to -2 plus √2, that whole quantity cubed. So it looks like in your book, they put it in decimal form. I probably would have, if I didn't let you have a calculator, you couldn't do that without a calculator. And I would just say, leave it in the exact form like this.
So I also have a question about this one, okay. About the answer to this one. So you can't cube a square root?
You could. The problem, which I think you might be thinking of, we can't just go ahead and cube the -2 and cube the -√2. We would have to rewrite this as -2 minus √2 3 times. We'd have to go through and distribute. So I'd have to, distribute, combine like terms, and then I'd have to take that thing and multiply it to the -2, my -√2. So, I mean, I could do that. It just would take me a little while. So I wasn't going to do it.
Sounds good. So on like a test or something, it would just be -2 minus the square root of 2 cubed.
Yep.
Okay, cool. Thank you.
Yep. But look and see when on the homework how they want you to write it. So they probably said, put it as a decimal and round it to the hundreds or whatever.
So how would you put that in a decimal if you didn't have a calculator?
You wouldn't.
You wouldn't. Okay. Okay.
Yeah.
Yeah. There's been a couple of questions. Like I got another one that was right next to something like this, and it ended up being the square root of 80 minus 320, and they wanted it in decimal, and I couldn't figure out how to do the square root of 80 in my head.
No. So I guess there's some stuff in there that I wouldn't worry about you guys doing that.
Okay, great.
And if it gave you some ugly answer like that, I would let you, leave it like this. But although I would want you to pull out factors that are perfect square underneath the radical, but then you would just leave it in that form.
Okay.
Other questions you guys want to look at? So that's probably one of the harder sections that we were doing so far. So maybe a little bit of relief today, hopefully. We're looking at inequalities and solving inequalities. So let me just pull that up. So first, let's talk about inequality notation, interval notation. A lot of times in mathematics, or at least in calculus and stuff, it's nice to put things in interval notation. And I personally like interval notation a lot. So a couple of things that can happen. First of all, we can have maybe x is greater than a. This is an inequality. The interval notation. Actually, let's graph it first. You should be able to graph these on a number line. So you would go and you would find a on the number line. And this is saying this is greater than a, so it's everything that is bigger than a would work. This is strictly greater than a, and so here, there's a couple ways that you can notate it. You can do an open circle, or you can do a parentheses. And I'm just going to do the parentheses just because that's kind of helps with the interval notation. So an interval notation sometimes looks like a point, but it's not. It could be just two numbers. It's going from smallest to largest. We're not actually including a, so we use a parentheses when we don't include the end value of the inequality. Put the smallest value you're coming from, so a. And then this is not stopping at any number. It's going to positive infinity. Around the infinity or negative infinity symbol, we always put parentheses because it doesn't stop or include any number there. If this had been x is greater than or equal to a, only difference here is instead of that parentheses at a, is that we have a bracket. And that should clue you in that you are including that value of a as part of the solution set. So same thing with interval notation, is either parentheses or bracket, depending on if you're including or not. So we're including a, so a bracket, a, comma, infinity. So same sort of idea with less than. We can have x is less than b. You locate b on the number line. This time it's everything that is less than, so shade to the left of b. And again, it's a parentheses. You're always going smallest to largest. So we're coming from negative infinity. And we're going to b, but not including. So with a less than or equal to, instead of the parentheses, we have a bracket and shade everything to the left. We can also have what is called a compound inequality. So that's where our solution is between two values, maybe including or not including. So we could have a is less than x is less than or equal to b. So in this case, we have a, we have b on the number line. Tells us that our x value, our solution is anything between a and b, including b, so a bracket there, but not including a, so a parentheses there. So you could have different combinations of those, that compound inequality, but just as if it's doesn't have the equal to part underneath the inequality, it's a parentheses, and if it does have the equal to part underneath the inequality, you put a bracket.
Professor?
Yes.
Is this 1.5?
Yes.
Okay.
And then there are rules for inequalities. Let's see if I can move. Okay, so when we're solving linear inequalities, and we'll talk about later, nonlinear inequalities are a little differently how we solve those. And actually today we'll talk about absolute value inequalities. But right now when we're solving inequalities, we use pretty much the same rules that we would do if we were solving a linear equation. We want the variables to one side, constant on the other side. So basically, if you have a is less than or equal to b, we can add both something to both sides of the inequality, and it would still hold true that a is less than or equal to b plus c. So if we add something to both sides, that's okay, and our inequality stays the same. We could subtract something on both sides of the inequality. Our inequality is going to stay the same. Oops. So a minus b . I don't want b. I want C. So A minus C is the same thing as B minus C. The other things that we did to both sides to get the variable by itself was multiplying or dividing by a number. This is where we have to be careful. It depends on if the value you're multiplying or dividing by is positive or negative. And so let's say C is bigger than 0. Then if we have A is less than B, then A times C is less than or equal to B times C. But if C is less than 0, then we have A times C is flip our sign greater than or equal to B times C. Okay, so these are stipulations if we had started with the value of A being less than or equal to B. So multiply or divide by a negative number. Remember to flip the inequality sign. Okay, so just pull one. Okay, so the following reads, solve each inequality, express your answer using set notation or interval notation. Oh, so maybe we should go back up and look at set notation. I think your book actually, this book might like that a lot. Okay, so set notation, let's just go back up to where we had done the inequality and the interval notation. Set notation. So sets usually are denoted by a, I call curly bracket. And then we're talking about what variable. And so in this case, we're looking at X. You will see a vertical line. That vertical line reads like such that. So this is a set of values of X such that, and now you give your stipulation of what has to be true for X. So in this case, X has to be bigger than A. So to me, it's almost the same thing as just rewriting it as the inequality notation. You just have your stipulations in there. So here we would just say the set X vertical line such that X is greater than or equal to A, etc. Okay, maybe you guys can give me some pointers. Okay, so we're looking at an example here. We have 8 minus 4 all times 2 minus X is less than negative 2X. Okay, so again, this was asking us to rewrite this, solve this, put it in interval or set notation, and graph the solution set. So again, you're going to solve this just like it was an equal sign in there. The only thing we have to be aware of is if we multiply or divide by a negative, it's okay to subtract a number. But if we multiply or divide, we're going to change the sign. So just like with a linear equation or any equation, usually you clean up both sides by distributing and combining like terms if possible. There's no sign between the 4 and that parentheses. So we're going to distribute. Carry the sign in front. So we're going to distribute a negative 4 to both terms. So bringing down the 8, we have negative 4 times 2. That gives us negative 8. Negative 4 times negative x, that's positive 4x. This is less than negative 2x. Well, 8 minus 8 cancels. And so we have 4x is less than negative 2x. I want all terms with a variable on one side, all terms without the variable on the other side. We'll only have terms with variables. Let's add 2x to both sides. So we have 4x plus 2x is 6x is less than 0. Let's get x by itself. And so if we divide both sides by 6, we get x is less than 0 over 6. It's okay to have 0 in the numerator as long as there is a number other than 0 in the denominator. And that is just 0. So x is less than 0.
Does the sign flip?
Excuse me?
Does the sign flip the other way because we divided?
No, because that we divided by a positive number. And so if this had been a negative 6, then we would have to flip it. So only when you divide by a negative or multiply by a negative do we have to worry about the inequality flipping. X is strictly less than 0. So go from 0, shade everything to the left. And it's strictly less, so it's going to be a parentheses here. And another way to write this is negative infinity, comma, 0, not including 0, so parentheses. Or x such that x is less than 0. So 3 things, 4 things expressing the same thing. So if you have a compound inequality, so you have multiple inequalities there. So maybe I have 1/2 is less than or equal to, our numerator is x plus 1. And this is all over 3. And then this whole thing is less than or equal to 3/4. So again, we're just going to solve this similar to what we had done before with equations. Only thing is we have 3 sides. Usually we didn't like having the variable, or sorry, not variable. We don't like having the numbers or denominators. And so we can clear that just like we had done before, clearing our fractions by multiplying by the least common denominator. And so if I look at 2, 3, and 4, and I think of the smallest number they all divide into, this would be 12. So that's a positive number, so I don't have to worry about when I multiply everything through by 12. So I have to multiply this by 12, I have to multiply this by 12, and this by 12. It's positive, so we don't have to flip the inequality. And then start canceling what they have in common in the numerator and denominator. So 2 goes into 12 6 times. And so we're left with 6 is less than or equal to. And then over here, 3 goes into 12 4 times. So technically we need to distribute that 4 to the x plus 1. So let's distribute it and rewrite it. So that would give us 4x plus 4. And then this is less than or equal to, 4 goes into 12 3 times. So we're left with 3 times 3, which is 9. So we could split this up as 2 separate inequalities while we were working this, but to me it just seems easier. And we can only do this because there's not variables on the left and the right of this sandwiched inequality. But anyway, so leaving like this, I could subtract 4 on all sides to get x by, I'm trying to get x by itself in between. So 6 minus 4 is 2, is less than or equal to 4x, which is less than or equal to 9 minus 4, which is 5. I don't want the 4 in front of the x, so we could divide all sides of the inequality by 4. So 1/2 is less than or equal to x, which is less than or equal to 5/4. or bracket 1/2, comma, 5/4 bracket. And so we would shade everything in between 5/4 or 1/2 and 5/4. Okay, so this book actually talks about, and my previous book I've never seen this before, but until recently in calculus. If you have A is less than B, sometimes it's helpful to compare the reciprocal. So if we have A over is less than B, what do we know about 1 over A? What is that to 1 over B? Any ideas? Would it remain less than, or would it flip the inequality?
I would guess it would flip since you're dividing by a bigger number.
Right, so you're dividing by a bigger number, so that's actually a smaller number. And so when you're looking at this in the reciprocals, we flip our inequality. Does it matter? And I'm sorry, I should probably, no, that's not right. There we go. Okay, a couple other ones. If A is greater than 0, then wouldn't it make sense that if you put 1 over A, well, if you have a positive number and you put 1 over a positive number, wouldn't that still remain positive? So if we know A has to be greater than 0, then we know 1 over A has to be greater than 0. If A is less than 0, then it would make sense that 1 over A is still less than 0, because 1 over a negative is a negative. Let's say if B is greater than A, and this is greater than 0, then we know that if we look at 1 over A, that's 1 over a bigger number is actually smaller than 1 over B. How do I do that? B is bigger than A, then 1 over A is bigger. Then, sorry, 1 over A is bigger than 1 over B, which is bigger than 0. Right. So if B is bigger, then 1 over A is bigger. These are both positive, so 1 over A and 1 over B is going to still remain positive. If A is less than B, is less than 0, then 1 over B is less than 1 over A, which is less than 0. Which kind of makes sense if you think about the number line, and numbers that are further to the left of 0 are going to be smaller. Oops. Okay, let's use this fact in here to help us solve the following. we have 2x minus 1. This is all raised to the negative 1 power is greater than 0. Okay, so rules of exponents. If you have a negative exponent, we can make that positive by bringing it down to the denominator. And this technically is saying the same thing as 1 all over 2x minus 1 is greater than 0. But we're going to use the rule that if something is greater than 0, then the reciprocal is also greater than 0. So we're going to use that fact. So, but if a is greater than 0, or let's say 1 over a in this case is greater than 0, then a has to be greater than 0. So let's use that and say, well, then we know that 2x minus 1 has to be greater than 0. To solve this, we're going to add 1 to both sides. So you get 2x is greater than 1. Divide by 2. We're dividing by a positive, so we're okay. So x is greater than 1/2. So we're looking at things getting close to 1/2, but not including. So parentheses 1/2 to infinity. So if you have 0 is less than parentheses 3x plus 6. This is raised to the negative 1 power. Oops. And this is less than 1/3. Okay, so we have what we have is greater than 0. If we want to, we can look at the I would probably do this something. I would approach this differently, but I believe your book wants to do it using those properties. And so we can look at this as the reciprocals. I really can't have a reciprocal though of 0. I know though that if I take the reciprocal, that this here, let me just write it. This is going to make it bigger. And so then I'm going to have 3x plus 6 is greater than 3. I also know that this is going to be bigger than 0. So let's just solve. And so if we get x by itself, subtract 6 on both sides, we get 3x equals negative 3. Not equal, greater than negative 3. Divide both sides by 3, we get x is greater than negative 1. And then solving for this piece, we get subtract 6 on both sides, 3x is greater than negative 6. Divide both sides by 3, and so we get x is greater than negative 2. So technically, if I look at this, this is an and statement. And statements mean that you're looking at the intersection of the two sets or what they share in common. And so if we look at this, if I looked at the number line, this tells me this first one, x is greater than -1. I'm going to shade it above. And then this piece says x is greater than -2. So basically right here. So if I was to shade what they shared in common, where they overlap in shading, that's going to be from, and not including, -1 to infinity. So our solution is -1 to infinity. Or another way to write it, x is greater than -1. Okay, so any questions over solving inequalities? Okay, actually, I see a challenge problem that I like. So this was one I liked. Like I said, I just changed this textbook so that it encompassed both trig and college algebra. But the textbook that we've been using in the last 4 years, when they talked about inequalities or compound inequalities, they had variables on both sides. So let's look at one of those. And they call this a challenge problem. So we have x minus 4 is less than 2x minus 3 is less than or equal to x plus 5. And that x plus 5 is all over 3. So it can't do what we were doing before with these compound inequalities where I was, isolating that x inside in between those two inequalities. I can't do that because of variables being on all sides. It wouldn't happen. And so what we have to do is we actually have to split this up as two separate inequalities. But we know that x minus 4 has to be strictly less than 2x minus 3. And this 2x minus 3 must be smaller than x plus 5 over 3. So and again means intersection, so taking what they both share in common at the end. So just solve them separately. And so let's look at this first inequality, x minus 4 is less than 2x minus 3. So I want variables to one side, constants on the other. I tend to like my variable when I'm dealing with inequalities on the left-hand side. To me, it just makes more sense. So I'm going to do that. So let's subtract 2x on both sides of the equation to get x on the left. And let's add 4 to both sides to get the constant on the right. So if we do that, we have x minus 2x is negative 1x. This is less than negative 3 plus 4, which is 1. I don't want a negative 1, but to get rid of the negative 1, I have to multiply or divide by a negative, and so that flips my inequality sign. So I get x is strictly greater than negative 1. So on the number line, is it strictly? I guess so. On the number line, we have from negative 1 to infinity. And I'm going to draw it above so I can just see where they overlap. Okay, so looking at the other inequality, let's first clear the fraction. So let's multiply both sides by 3. So let's distribute the 3 on the left. So we get 3 times 2x is 6x, minus 3 times 3 is 9, is less than or equal to x plus 5. Get variables to one side. So if I subtract x on both sides, add 9 to both sides. So 6x minus 1x is 5x. Is less than or equal to 5 plus 9 is 14. Divide both sides by 5. That's a positive number, so we're okay. It's going to remain less than or equal to. This is 14/5. It helps you write it as a mixed number. So that's the same thing as 2 4/5. Or 2.8. Okay, so locate 2.8. On the number line. This is a bracket. And it's everything to the left. So look at what they share in common, and that is your solution set. So they're sharing everything between -1, but not including -1 to 2.8. Or -1, parentheses, -1, comma, 2.8 bracket. Or -1 is less than x is less than or equal to 2.8. Okay, so that is 1.5. And 1.6 is pretty much the same, except dealing with absolute value equations and inequalities.